The first chi-squared test that's normally studied is chi-squared goodness of fit, which is what this 2008 question number 5 is corresponding with. So looking at moose and which region they're found in a large burned area. So split into 4 different categories. Inside, like really in the middle. 2 is in but near the edges, outside, close by, and 4 is really as far away from the burned area as possible. Figure not drawn to scale. So the proportion of total acreage in each of the habitat types was determined for the study area. So we're observing the moose that are there, and the proportion can just be measured. That's not going to change. So the researchers who are conducting the study expect that the number observed will be proportional. And so since we're given these proportions and we want the breakdown to be the same, that's what makes it a goodness of fit. So assessing the goodness of the fit. How well does it actually match what was given? So are these data consistent with that? Conduct the test. We're not going to assume the conditions were met for all of it because this is new for us and we need to practice that. And then a follow-up question just relative, what habitat types do they seem to prefer? So we are looking at the habitat type being proportional to the amount of acreage there. So I'm going to do a little bit of mix between handwriting. So this is a chi-square goodness of fit to identify the type of test. Our null hypothesis would be that the proportion of moose is for habitat type. So observed in habitat type. So the proportion of moose observed in the habitat type is equal to the given proportion of acreage for the burned area. And so this then, knowing that really the proportions of them observed in each, we'll say habitat type, is equal to the given proportions. So it's recognizing that all 4 of them are as they should be. So this could be, sometimes we'd think, why can't we just do a proportions test with this? But the issue is that you can't do multiple tests where this is happening. And so it's not that any one of the 4 is off, or that all 4 of them are off if we were to test one each individually. But the alternative for goodness of fit, we can typically say at least one of them differs. So the conditions that we're dealing with, we have random like always, and independent like always. So we won't review how to do those because they are the same as they always are. So our large counts condition for this one, the expected counts need to be at least 5 for our sampling distribution to be modeled by a chi-squared curve. So expected counts. We have the observed counts listed here. So we observed 117 moose in each of these 4 different habitats. We need to look at each of them and break down if they're proportional the way that they should be. Then looking at habitat type 4, 45.5% of my 117 moose should be in habitat 4. So it does happen to be the highest number that's there. But then you can see the discrepancy if I have a proportion of just over 10% in habitat 3, but that's the second highest concentration of observed moose. So When we're working with chi-squared, we're always dealing with just the expected counts and observed counts. And so we find them based on what was given here for the proportion. So we have the number of moose at 117, and I have these stored into my calculator in a list. So areas 1, 2, 3, 4, my observed is in list 1. I have the expected proportions in list 2. So I'm going to take in to list 3, and I need 117 of each of those proportions calculated. And so these are my expected counts. So I would expect, if the acreage is 34% of the total space, 39.78 moose to show up there. I only had 25. And then again, the highest one in Habitat 4, I would expect 53 of them. So these are my observed and expected counts as given. All of my expected counts are at least 5. I need to show this on my paper. My expected counts need to be at least 5. And so this typically is done just by listing them with where the observed counts fall. For the sake of space and time, we're going to jump to the do step and look at the formula. So my chi-squared statistic is going to be the sum of each of those. So the sum of my observed minus expected squared. So how far away from what should have happened are my observed counts. And then, like we've done in the past, we square so that it's positive. And then relative to what I'm expecting, I divide by my expected counts there. So if I had 25 in habitat type 1, and I was expecting 39.78, then that's the first component of my chi-squared statistic. I would do the same thing for habitat 2 and habitat 3, and then finally habitat 4, where I had 40, and I was expecting 50 some, so 53.24 we'll call it. And this value then is my chi-squared statistic. So it does not matter which type of chi-squared test you are performing. This is the same work for all of them. Observed minus expected squared. Again, how far off is it? Make it positive, and then relative to what should be happening. Here's my expected count. So with goodness of fit, this is easy enough to do with the lists in the calculator. That option is there to just take quantity list 1 minus list 3, square it, and divide by list 3. So I can get my test statistic that way. Older calculators don't have a chi-squared goodness of fit, so this really was the best method for doing that. Let the calculator at least do a little bit of the work for us. So this gives me each of my individual components, and I can see then how much farther off one is than the other. I want the sum of those 4 values though. And I could have stored those components in a list somewhere. I have a giant result here. This 43.689 is a really big test statistic. And so I'm going to have very strong evidence to reject the null hypothesis. And so the issue then becomes if I have to go to the table and figure out the degrees of freedom. I have 4 categories. I had 4 habitat areas. And so my degrees of freedom are categories minus 1. So since I had 4 areas, I have 3 degrees of freedom for this one. The p-value, when I look at this on the table, is going to be off the charts because that's so big. And so I would just say essentially 0. Or if I wanted to go to second distribution, which was where we hold beloved our normal CDF and inverse norm, there is a chi-squared CDF that I could use. So I could take a look at this. My lower is always going to be the test statistic, and then upper is some very large number, whatever that may be, in my degrees of freedom. And so I can see how ridiculously small my p-value is here, written in scientific notation. I would, and we will absolutely do it with the other chi-squared tests, go to our other favorite place, which is the stat test menu. And there is a difference here. So the chi-squared test, if there's an older calculator, that might be all that you have. We'll deal with that in the next lesson. Those have to be in matrices. The chi-squared goodness of fit, you have to have the observed and expected into a list already. And so we have that in list 1 and list 3. I'm not using those proportions that were given anywhere. Those were converted into counts. And if you read through the book or anywhere else, one of the tips that they always give you is to make sure that you're working in counts. It's absolutely fine that the counts are decimal points for what's expected. But in order for the calculator to recognize this, they do have to be counts. One other thing that can happen is that you could have 0 for one of your observed counts. So we could have not had any moose in one particular space. So this gives me that same test statistic. My p-value of something ridiculously small. So when we write our conclusion, we can say it's essentially 0. So 1.7 times 10 to the negative 9th. And then one of the follow-up pieces now. So this created that contributions list, which was what was on my screen when I did list 1 minus list 3 quantity squared and divided by list 3. With chi-squared, there's something called follow-up analysis. So if I go to second list now, I can see that contribution list was already created and saved for me. So I could put this in my stat editor to look at it, or I could from here just scroll. So 5 something, 8 something, 26 for that third habitat space, and then only 3.29, which again, I had the highest number of moose there. I had 40. And I had the highest proportion of acreage there. And so it makes sense for that to be my biggest one. The third space, though, should have only had around 10%. It said the second highest count of moose. So that's a big contributing factor as to how far off my values were from what was expected. And because chi-squared is always a skewed right distribution, as it gets bigger and bigger, those components are what I'm looking at. So whenever follow-up analysis is identified, that's what it refers to. That's what we're talking about. So for my conclusion, we have very strong evidence to reject the null hypothesis at any significance level if the proportions of moose in each habitat area are proportional to the acreage in each area, we would see observed counts such as ours about 0% of the time. So standard conclusion, what we've always done, it's just longer because, again, the hypotheses are usually written in words. The follow-up for this question, relative which ones did they seem to prefer, this, again, was the idea that we had more observed than we were expecting in areas 2 and 3. So if you take a look at the scoring guidelines, you'll be able to see some of the differences. I went for the second writing of it. The no preference, I feel like, is an unusual one. And this third option down here where you can pick each of the proportions is just an awful lot of work. The test statistic is there. You can see the full work written out with those degrees of freedom again, and then p-value, not consistent, strong evidence. So for option B, it's just recognizing that relative to those proportions, they were much farther off, and because they were larger than what was expected as opposed to less than, which was what happened for 1 and 4. So this, again, chi-squared goodness of fit, you have to be given values, and we work through list operations with them. Expected counts hopefully make a lot of sense. We're just breaking down the total count that we had for each of those proportions, so it's an easy multiplication step. They can be decimal points. That's not an issue. And for this one, we kind of work in order. You'll see for the next lesson that we sort of work backwards for the other two types of chi-squared tests.